So, what is meant by specific heat capacity? The specific heat of a substance is the amount of heat needed to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. In the SI system, water has a specific heat of 4,184 joules per kilogram degree Celsius, which is a large value compared to the other substances. In another system of units, the specific heat of water has the value of 1 calorie per gram degree Celsius, which is the amount of heat, which is Q gained or lost by a substance, is Q equals to mc theta or T, where C is the specific heat, M is the mass, and T is the change in temperature. The specific heat of a substance can be determined by the method of mixtures, where a hotter substance will be mixed with a substance at a lower temperature. When hot and cool substances are mixed in an insulated container, such as a calorimeter, heat will flow from the hot to the cool substances. The purpose of this experiment is to determine the specific heat of different metals, to understand the concept of heat capacity, and to learn how to calculate specific heat capacity. And for the hypothesis, specific heat capacity is vary between metal. Copper have a higher heat capacity, followed by copper and brass metal.
So now I will be explaining about theory. Specific heat capacity is the amount of heat energy required to raise the temperature of a substance per unit of mass. In SI units, specific heat capacity C is the amount of heat in joules required to raise 1 gram of a substance by 1 degree Celsius. It may also be expressed as joule over gram degree Celsius. The change in temperature delta T of a substance is proportional to the amount of heat delta Q added or removed from it. So, in equation form, we may write as delta Q equal to C delta T, where the constant of proportionality C is called the heat capacity of the substance. However, the amount of heat required to change the temperature of an object is also proportional to the mass of the object. Hence, it is convenient to define specific heat capacity C, which is the heat capacity per unit mass of a substance. Thus, equation will become delta Q equal to C times M times delta T, or C equal to delta Q M times delta T. By measuring the temperature change of a given mass of substance produced by a quantity of heat, the heat capacity of a calorimeter and specific heat of a substance can be determined experimentally. This procedure that uses calorimeter known as the mixture method. If several substances at various temperatures are brought together, the hotter substances will lose heat and the colder substances will gain heat until all the substances reach a common equilibrium temperature. If the system is insulated so that no heat is lost to the surroundings, then by the conservation of energy, the heat loss is equal to the heat gain. This experiment started with an empty calorimeter at room temperature is filled with a known mass of hot water. Then the mixture temperature is measured. So we may write as heat gain equal to heat loss, delta Q calorimeter equal to delta Q water, and C delta T calorimeter equal to M times C times delta T water. Then, a hot metal is added to water in a calorimeter cup, and the mixture is stirred until the system is in thermal equilibrium. The calorimeter isolates the systems from losing heat. In mathematical form, we may write as heat loss equal to heat gain, delta Q metal equal to delta Q calorimeter plus delta Q water. mm times cm times in bracket Tx minus Tf equal to in bracket C calorimeter plus mw times cms times in bracket Tf minus Tw, where Tx is the initial temperature of hot metal, Tw is the initial temperature of water, and Tf is the final equilibrium temperature of a mixture. As we can see, water is the source that were being used in the heat exchange for this experiment. It is because water has a very high specific heat compared to most other substances. Thus, water is commonly used as a coolant for machinery because it is able to absorb large quantities of heat. This is one of the reasons why manufacturing, power plants, etc. located near water sources, because cool water is pumped into the plant, while warmer water is pumped out of the plants. Apart from that, coastal climates are much more moderate than inland climates because of the presence of the ocean. Water in lakes or oceans absorbs heat from the air on hot days and releases it back into the air on cool days. The material that were used in this experiment is calorimeter set, hot water, beaker, metal blocks, heater, electronic balance, thermometer, and water at room temperature. So next we move to the procedure. Firstly, hot water was prepared at the beginning of the experiment and heat until it boils. We used hot water is to save time for boiling. Next, calorimeter set was weighed and its mass was recorded using electrical balance. After that, all the metal blocks also were weighed and their mass was recorded. Then, 100 ml water at room temperature was poured into calorimeter and left for about 1 to 2 minutes so that the temperature is stable. Then the initial temperature was measured and recorded. Next, a calorimeter set with water was weighed, and the system and its jacket were insulated. In other hand, a string was tied to the all metal blocks and was placed into the hot bath to heat it one by one. Then the temperature of the water was measured with a thermometer. It will be assumed that the temperature of the metal is the same as the boiling water. Last but not least, the metal block was removed from the boiling water and immediately placed into a calorimeter. Then, water in the calorimeter was stirred gently by using a stirrer. The equilibrium temperature of metal and water was measured when the temperature stopped rising.
Okay, so now let's move to the next part of this experiment, which is the result part. This is the result that we must note and get after we do the experiment. First data that we can get is the mass of calorimeter with stirrer, which is 0.2299 kg. The mass of calorimeter with water is 0.0339 kg. The mass of metal 1 is 0.095 kg, second metal is 0.062 kg, and the last metal is 0.066 kg. The initial temperature of metal 1 is 98.5 degrees Celsius, while the initial temperature of the second and third metal is the same, which is 100 degrees Celsius. After some calculation, the changes of temperature of metal 1 is 68 degrees Celsius, metal 2 is 66 degrees Celsius, and metal 3 is 66.5 degrees Celsius. As for the calculation of specific heat capacity, we can use the formula to calculate the specific heat capacity for the three of the metals block. The MW that we get is constant, which is 0.04 kg. The CW is also constant, which is 4189. The MCS is 0.230 kg. The CCS is 389. The MX is the weight of the metal that we want to calculate, and the TX is the block temperature. For metal 1 calculation, we put all the data we get into the formula, and we will get the final answer is 125.45 joule over kg degree Celsius, which make it as a lead metal. Next is the calculation of metal 2, and we get 390.26 joule over kg degree Celsius, and this value make it as copper metal. And the last metal block specific heat capacity that we get from calculation is 318.37 joule over kg degree Celsius, which make it as a brass metal. We calculated the specific heat capacity of three metals in this lab. We used copper block, lead block, and brass block as metals in this experiment. We immersed these blocks in boiling water for 10 minutes. To achieve the same water temperature, 100 degrees Celsius, once the blocks reach the proper temperature, we place them in a cup of room temperature water, just enough to cover the metal, to produce more accurate results. We measured the temperature of the starting water and calculated the temperature change after adding the blocks. We were able to determine the specific unit of heat capacity of three metal blocks using the masses of the blocks and room temperature water. The specific heat capacity of water 4186 and the temperature changes of the water and the metal blocks. There is no heat loss to the environment, as energy exchange occurs only between the object of interest and water. There is no heat loss to the surroundings. In relation to assumption, there is only a negligible transfer of energy to the container's walls. This is the energy transferred to the calorimeter itself, which is still a part of the system. Each method causes the temperature of the water to rise to a different final temperature. According to the table 1, the specific heat capacity of aluminum is the highest. It is followed by iron, copper, and brass. This indicates that each metal that absorbs the energy in a different way. The data obtained from the experiment for the metal block 1 is 125.45 joule over kg degree Celsius, which makes this metal known as a lead if you refer to the table of specific heat capacity of the metal. And the metal 2 is 390.26 joule over kg degree Celsius, which is a copper, and the last metal is 318.37 joule over kg degree Celsius, which makes it a brass metal. Our final results contain an error because the number we calculated for our heat capacity did not match the correct value for the specific heat capacity metal we used. In order to determine the source of error, we suspected that there was too much water in the cup. A significant temperature difference when there is too much water in the cup. Because the specific size metal can only heat to a certain temperature, the final temperature must be precise, a certain amount of water in proportion to its size. Okay, lastly is about the conclusion. For this experiment, the result is acceptable. The purpose of this experiment is to determine the specific heat of metal. The apparatus that was set up to record the calorimeter mass. The mass of the metal block was also measured. The heat bath was then heated. The metal block is carefully immersed in the heat bath and transferred to the calorimeter. As we do the experiment, we managed to calculate the specific heat of the metal block lead, copper, and brass. When some of the hot water is carried into the calorimeter, the uncertainty usually occurs. This has the potential to alter the temperature inside the calorimeter. Another is that when the water in the calorimeter splashes away while inserting the metal block, the mass of the water changes. As a result, with proper handling, the energy can still leak within the calorimeter. Based on the result that we get, we can say that this experiment is successful.